Day 74. We're going to start off by reviewing what we've learned so far in this chapter, and then we'll take some new notes on earthquakes, and whatever time you have available, we will finish up our fault models and show them for a grade. Please remember this is going to be for a project grade, so it's a larger number of points. Well worth your time to get those finished. Okay, let's first review the different layers of Earth. On the outside, we have continental crust. Let me cover some of this stuff up so that it's not quite so much material to look at all at once. Okay, so continental crust over here is the thicker layer underneath the mountains and land and places where we build houses and all that kind of stuff. Continental crust. Over here we have oceanic crust that's underneath the water of the oceans. This is where the ocean rigs, the oil drilling rigs, will go through and be drilling into the oceanic crust. So would you please draw a little ocean oil rig here drilling down into the oceanic crust. And then below that we have the mantle. The mantle is a section underneath the crust, whether it be the continental crust or the ocean crust. And the mantle is a flexible solid. Please write down flexible solid. Since it is flexible, it can flow in convection currents. So hot mantle can rise up and cool mantle can sink. So we have these things that have been going around and around and around in the mantle. The upper part of the mantle, along with the crust put together, is called the lithosphere. The lithosphere contains the continental crust and the ocean crust and the upper mantle. The upper mantle is not as flexible as the lower stuff, and so we can lump it together with the crust in some situations. Below the lithosphere, we call the mantle the asthenosphere. This is much more flexible, and this is where the convection currents are really working well. Below the mantle, we have the outer core. And the outer core is liquid. So let's draw some squiggly lines in here to represent liquidness in the outer core. And then finally, we have the inner core. And the inner core we think is solid iron. Second page. We have the concept of plate tectonics, where the continents are moving around on the surface of the Earth. And the guy named Wagner was the first guy to really become famous for this idea. He's not the first one to think it, but he's the first one to scientifically publish it and produce some evidences for it. And one of the evidences that he really latched onto was the shape of the continents, particularly South America and Africa. So I want you to write the word shape here. The shape of that coastline and the shape of this coastline seem to fit together. So would you please write those two words with arrows showing that the shapes fit. Next, I want you to make a little region here and draw a little fishy symbol there, and then draw a region over here with another little fishy symbol. And what this represents are the fossils. They found some fossils of freshwater fish here and some freshwater fish over there, and these fish would not survive a trip across the salty oceans. And so most likely then they think that these two continents were together at one time, and the fish were just swimming around in the lakes and rivers, and then sometime in the past, continents divided, and so that's why we have these fossils on such different places. So let's write down the word fossil fish, and over here, fossil fish. Next, mountain ranges. There's some Appalachian Mountains going up in that part of North America, and those kinds of mountains continue over into Europe. And the same kind of rock folds, same kind of minerals and all that kind of stuff. And so it really looks like those guys were connected at one point, and then the lands separated and broke them apart. The other thing that Wegener looked at was that down here we had some fern fossils. So why don't you go ahead and draw a picture of a fern there. And we also had some lizard fossils. So I'm going to draw something like a lizard here. And the lizards and the ferns would not survive in such a cold climate of where Antarctica is now. And so Wegener thought, well, that must have meant that Antarctica had been in a different place in the past, closer to the equator where it's warmer, so that these kinds of organisms could survive. So it must have moved to the current location sometime in the past. Okay, off to the side here, what I want you to write down is the word Pangaea. That is the name that Wegener gave the one giant supercontinent when all of these lands were connected. And let's write those sentences. Pangaea split by unknown forces. Wegener did not know what caused Pangaea to break apart. And that's one of the reasons why very few people believed him and accepted his theory during his lifetime. It was only after he died that people thought about these giant convection currents in the mantle that pushed the continents from below. Okay, the last thing to review is the types of boundaries and the way that things move. So the first thing at the top, I want you to see that we have plates moving apart, and that causes something called a normal fault. A normal fault is formed when we have a diverging boundary. In a diverging boundary, we have things being divided. One thing going left, one thing going right. The land is split apart. So please write down those words: diverging, divided, split. We have all these I words or div words to connect together. The next kind is a converging boundary with no subduction. Converging boundary, that's when the forces are coming together, pushing together. They are colliding. We have all of these CO words: converging, come together, collide. This is without subduction. And mountains are made when these continents slam together. Next we have a converging boundary with subduction. And with subduction, the plates come together again, just like we did before, converging, come together. Only this time, one of the plates goes down like a submarine underneath the other plate. And lastly, we have a transform boundary. Here the rocks are not being pressed together at all, and they're not necessarily being spread apart. They're just sliding together like your hands rubbing to get warm. They're not pressing terribly together, just a little bit. So mountains are not necessarily being made here. And that's the end of the review. Let's look at the new notes. What is an earthquake? An earthquake occurs when forces are so great that the lithosphere breaks. This releases a large amount of energy and causes seismic waves. The plates are pressing against each other, trying to get apart, but every once in a while, by the shapes, like jigsaw puzzles, they get trapped and pressure builds, and suddenly it moves over a little bit more. And that sudden movement causes the earthquake waves. They get jammed, and when they snap to another place, then the waves are made. The land can move a few feet at a time. I've heard of earthquakes moving land in California 3-4 feet, something like that, in a single earthquake. Here's some vocabulary that is important to understand. We have the focus. That's the place where the rocks are actually slipping. And the epicenter is location on the surface right above the focus. So that's where the earthquake waves are going to be the most severe. Types of waves. There are several different kinds. We're going to be looking at 3 of them. P waves, or primary waves. Those are push and pull. If I was to have a slinky over here and to demonstrate a push-pull motion, I would grab onto the slinky over here and jiggle back and forth, and you would see an area of compression here that moves down the slinky. This is the fastest kind of wave. It's the first wave to hit you in an earthquake. It travels underground, and it travels through liquids and solids. The next kind of wave is called an S wave. It is a secondary wave, and it moves side to side. So the S you can think of as meaning secondary. It's the second wave that hits you. Or you can think of it as an S for side to side. Either way it works. You need to know both of those things. It is also the second fastest. It travels underground mostly, and what matter does it travel through? It travels through solids only. It cannot travel through liquids, and that's one of the reasons why we're pretty confident that the outer core of the Earth is made out of liquids, because we cannot feel the S waves from earthquakes when these S waves hit that layer of Earth. The last kind of seismic wave that we're going to be looking at is an L wave, or a surface wave. An L wave is like a water wave. So you can think of the L as like water, or you can think of it as being the slowest, and so it is the last of the waves that we're studying, the last one to hit us. There are other kinds of waves, but this is the last one that we're going to be looking at. And this one travels mainly at the surface, and it causes lots of damage. So how do earthquake waves move? The P waves and the S waves start at the focus and move in all directions. The L waves start at the epicenter and then move in all directions. How do we locate earthquakes? All over the world, there are machines that record the waves created by earthquakes. The machines are called seismographs. Scientists determine the epicenter of the earthquake by using something called triangulation. For triangulation, you need the lag time graph and the seismographs from 3 different locations. The word triangulation has the TRI in the middle. That refers to the fact that we need 3 different locations in order to figure this out. We look at the earthquake from 3 different perspectives. Triangulation. So, how do we locate earthquake waves? Continued. We use lag time between the P wave and the S wave arrival to find the distance to the epicenter. The lag time is the difference in time from when the P wave hits us to when the S wave hits us. The P wave, remember, travels faster, It's the first one. And then the land calms down for a second, and then the S waves could hit us. If you know the lag time at a specific location, you can use the following graph to get the distance that that location was from the earthquake. This phrase is not in your notes. So let's try to make an analogy. Let's say that we're having races between a bicycle and a car. We have the starting line down here, and the bicycle and the car. And then we have different observers down the line. Here we have an observer who's 10 yards away from the starting line. The difference between the bicycle going by and the car going by is only going to be a few seconds. The bike is not going to be that far behind the car when you're observing it from only 10 yards away. However, as we go farther away, let's say we have another observer 100 yards away. Well, the car is going to get past that guy in just a few seconds, but the bicycle, it might take you a minute to travel 100 yards. So this observer would see the difference of time between the car and the bicycle being about a minute, let's say. Okay, then we have another observer who is 1 mile away. The car is going to get to this observer, again, in just like a minute or so. But the bicycle, it might be like 10 minutes before it travels the 1 mile to be seen by this observer. And so, these three different observers, being different distances away from the starting line, will see the bicycle and the car be farther and farther apart. So if I had an observer see the bicycle and the car, let's say 30 seconds apart, 30 seconds would be, about halfway between these two locations. So we would know that we would be about 50 yards away from the starting line if we saw them 30 seconds apart. If they were 1 minute apart, they'd be 100 yards away. If they were 10 minutes apart, they'd be about a mile away from the starting line. So what if we had an observer who didn't know exactly how far away they were from the starting line, but they saw the bicycle and the car 5 minutes apart from each other, the car first and then the bicycle 5 minutes later? Well, according to our data here, that would mean that the person was about a half a mile away from the starting line. So the farther away you are from the starting line, the farther apart the car and the bicycle will be as they do their little race. The same thing happens with seismic waves. The longer the time between the P waves and the S waves, the farther away you are from the location of the earthquake. And we can make a graph of this. So here is the number of minutes that is between the P waves and the S waves, and this is the distance that we are to the epicenter, or the focus, or in other words, where the earthquake started. So if I was 2 minutes apart, if the P wave hit me and then 2 minutes later the S wave hit me, I would go up to the 2 and follow over, hit this diagonal line, and come on down, and I would see that I was 1,000 kilometers from the focus or epicenter. If I was 2.5 minutes between the P and S waves, I go up to the 2, and here's the 3. I go halfway in between. That's like between these two lines. I'd have to estimate between the lines, go over to the diagonal line, and then come on down. And I'm at the second line past 1,000. So that'd be 1,200 kilometers from the epicenter. We're going to be using this graph in just a few minutes. Okay, here's what the seismic graph sort of looks like. As long as everything is calm, we have a nice flat line. The P wave will hit us, and then suddenly the S waves will also start to hit us. So we're looking for the lag time between when the P waves start and when the S waves start. Looking at the graph down here, or a table, from the Phoenix The P wave, there we go. The P wave hit right about here at the 160-second mark. The S wave hit at the about 280-second mark. So the difference, the lag time, is 120 seconds. Let's divide that by 60 seconds to make out how many minutes there are. So that'd be 2 minutes between those two waves. And according to this chart, at 2 minutes, we go over and down. That's 1,000 kilometers to the epicenter. So I put 1,000 there. For the Denver, Colorado seismograph, the P waves start at about 200 seconds. The S waves start at about 380 seconds. So I put those numbers down here in the chart. The lag time then is the difference between these, 180 seconds. Divide that by 60 seconds per minute to get 2.5 minutes. 2.5 minutes on our chart. We go up in the exact middle. It's going to be between these two lines on the graph. Go over, hit the diagonal, come on down, and once again that's at 1,200 kilometers to the epicenter. So in my chart I write down 1,200 in the bottom on the right hand side. For the Seattle, Washington seismograph, the P wave hit at about 100 seconds and the S wave hit at about 180 seconds. That's a lag time of 80 seconds. Divided by 60 to come up with 1.33 minutes. 1 1/3. So here's my graph. 1 1/3 will be the first line above the 1. Go over and down, and that's going to be at about 600 kilometers to the epicenter. So there's my data. And we're going to use these distances here to figure out exactly where the epicenter was. On this map, I've given you the circles. Here's Denver, Colorado. I'm sorry, let's go with Phoenix first. Here's Phoenix. And we know from our chart on the previous page that the earthquake was somewhere 1,000 kilometers away. So I made a whole bunch of dots, 1,000 kilometers in all directions from Phoenix. And then I connected all the dots to be a circle. So this circle represents all the places that are 1,000 kilometers away from Phoenix, and so the earthquake could be around any one of those spots. And then look at Denver, Colorado right here. And I put dots everywhere 1,200 kilometers from Denver. So all of these locations on this circle are 1,200 kilometers from Denver. We don't know where on this circle it is, but somewhere. And then Seattle had some data. Seattle, we said, was 600 kilometers from the epicenter. So I make this circle here. All of these places are 600 kilometers from Seattle. So the only place that would satisfy all these different requirements is this spot right here. This spot is where all three circles cross. It's 600 kilometers from Seattle, it is 1,200 kilometers from Denver, and it is 1,000 kilometers from Phoenix. And so that is the epicenter, where all three circles cross. So let's fill in this, the blanks. Now that you know the distance from the earthquake to the station, you draw a circle around each station with a radius equal to that distance. The epicenter of the earthquake is where the three circles cross. So let's write it on the map. Epicenter with an arrow right there. And lastly, the Richter scale. The Richter scale measures the magnitude of energy released during an earthquake. The Richter scale ranks the earthquake from 1 to 10 based on how high the waves on the seismograph move. The stronger earthquakes make higher waves and get a higher number on the Richter scale. And I also want you to know that each step of the Richter scale is 10 times worse than the bottom one. So a 3 is 10 times worse than an earthquake with a 2. And then to move up to a 4, you need to have a 10 times worse earthquake there. And keep on going. Each one is 10 times worse. The next bit is about the Mercalli scale, but we're going to skip that section.